This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
We built these inverters using the minimum length and width devices. How fast could we get it to run? And we've shown that and this is we're driving inverters running 3 other inverters, and here we're showing that you can run at approximately 66 gigahertz. Right, so that just gives you a little bit of intuition, some back of the envelope type of calculations, which allows you to check some of your parasitic extraction tools. Because one of the things that you do when you're designing some of these circuits is essentially you design the circuit, you write your Verilog or your VHDL. You synthesize it, you run it through the timing tool. The timing tool tells you that this is as fast as you can actually run it, and this is the slowest net, or this is the slowest section. And what you can actually do is now start building an intuition on how fast can it be, and what are some of the limitations. And in this particular case, what I'm saying is, for one of the most simplest of circuits, which is an inverter driving three other inverters on a 65 nanometer CMOS process, you can get 66 gigahertz. And I guess being at 66 gigahertz, I tried to make a joke, if I remember correctly, that it's very high speed electronics. That's why the name of this course. Now, what we talked about a little bit was we delved a little bit into some layout and talked about why sometimes we see that we've got twice as the amount of diffusion as we do in other cases. Like in this particular case, you've got a PMOS and an NMOS, you can't do anything. But if you had, for example, like in this particular case, 3 NMOSes in series, what you would do is you would try to choose or try to share the diffusion regions in order to be able to reduce the total amount of diffusion capacitance. Right, so even though you would be tempted in most cases to lay out your transistor like as such, which is an N well, and your gate in between, then put a large contact, bit of metal, and doing it again and again and again. That's grossly inefficient, and it actually makes the device run super slow, because now all of a sudden you've got twice as much capacitance that you didn't need to have. And essentially what I was saying is, if you've got these NMOSes or PMOSes, the same type of device in series, what you can actually do is actually share the diffusion wells in order to be able to reduce your overall capacitance and your diffusion capacitance. I won't go through the examples again. Here, what I did is went through a 3-input NAND gate, and we calculated all the capacitances and the resistances. And then I did another example where I had an input, a NAND, feeding some other NAND gates, and actually worked out what all the capacitances were, and showed what at least the Elmore propagation delay, or the Elmore equivalent circuit, is in order to work out the effective propagation delay for a rising edge signal. And then what we did was to show that there is a difference between a rising and a falling edge. What we did is we calculated the equivalent signal or the equivalent circuit, worked out the propagation delay, and showed that the falling to rising edge time of propagation delay is essentially the falling time. It takes is 1/118th of the rising time. Right, so therefore so the rise time is faster than the fall time. Okay, so that just gave you some of the machinery and some of the insights in order to be able to start understanding how can you start, if you had a couple of gates and you put them down, how can you work out some of the capacitances and resistances in order to work out the equivalent models, the equivalent Elmore delay model, in order to be able to estimate the propagation delay. Now, what we're going to do today is we're going to build upon this, okay? Now, the first thing that I'm going to go through, and I'm going to go through it very quickly, is essentially working through the effective resistance. Now, as you saw in these circuits when we were working out the equivalent model for a transistor, we had it as a resistor and a capacitor, right, in parallel. Now, what we're going to do here is, you know, a lot of times what happens is you get a data sheet, or you've got the process development kit model, which actually gives you current versus voltage curves, and essentially what you want to do is work out the effective resistance, and that's relatively easy to do, right? As long as somebody's shown it to you once, then everything's good, right? So what essentially you do is you have your drain to source current versus V out versus the various for the NMOS device, various gate to source voltages. And what you do is you have it between the device being fully on and the device switching on, right? Which is, in this particular case, I'm assuming it's about VT is roughly about 0.5. And what you do is you work out, you know, V out between the high and low and the difference in current, and you work out this gradient. And that actually essentially gives you your effective resistance for that device. Right? So that's all you needed to do. It's nothing spectacular, but given the data sheet and given a little bit of information, you can actually work out what your effective resistance is. Okay, now since we've recapped what we've done in the previous lectures, now let's move on to today's lecture. And let's switch on the lights. Now, what we're going to do is, we're going to look at more complex gates, and what we're going to do is we're going to use some of the information that's going to be available to us, right, in terms of, you know, a lot of times when you are designing a particular process or designing in a particular process using a particular standard cell library, people give you a whole bunch of information regarding the various gates. Does anyone know what a standard cell library is? Okay. All right. So essentially, when you're, for example, building on an ASIC or building on a chip, you can do two things. You can say, well, I'm going to design everything, including the, you know, all the gates by hand, by myself, or I can actually buy a library and somebody else in that library has designed for my particular process all the gates, right? And usually they've put a lot of effort in order to try to optimize those gates. Now, of course, there's always a trade-off, but you know, the gates are usually somehow optimized for that particular process. And it also, what it means is that when you're synthesizing your circuits, and usually the way that you do this is in a standard flow or a standard cell flow is you write your Verilog or VHDL. What do you guys learn in this course? Verilog or VHDL or none of the above? A little bit of Verilog. All right, okay. So essentially what you do is you do your coding in Verilog, and then what do you do once you've got your Verilog? Sorry? You did a calculator, but what did you do, right? No, I know you did that, but what's the process, all right? So you write your Verilog, and then what? Okay, so you got your Verilog. You did a architectural or a functional simulation first before you synthesized, and why did you do that? Okay, so functional simulation is when you've done the simulation, right? So there what you're trying to do is you've written some code, and all of us being human, and usually there's about, at least if it's software, there's about one bug every about 14 lines, right? What means that if you wrote a few thousand lines, there's many hundreds of bugs. Or many bugs, many tens of bugs. So what you do is you run it through this, you run a simulation where it's actually simulating, not the circuit, but actually just simulating your code, right? So therefore you're trying to show that the code that you've written is doing what you expect it to do, right? So then what you do, so this is what you would do even for an FPGA, right? Okay, so then you're happy, right? You say, well, I think I believe this. Now, the next step is you synthesize the code, right? And as part of the synthesis, what you're doing is you're converting the Verilog into logic gates, right? So therefore, you're generating your schematic, right, as part of your synthesis. Now, I don't know if you went through that as part of your process.
We synthesize it and look at how the circuit's like.
Yeah.
And find out, okay, there's a multiplexer and there's something there, but we just look at the code.
Yeah, but that's fine. Okay, so you've done your synthesis, right? Now, after you do your synthesis, usually you have to re-simulate, right? Because a lot of times you can think of situations where, you know, there could be, you might have synthesized a latch instead of a flip-flop, or you might have not had all the cases completed in a case statement or whatever. So what you need to do is you've got to make sure that the circuit that's being synthesized is equivalent, right, to the functional circuit that you wanted to produce, or the functional code. And there's also tools now that do that automatically for you. But essentially, in the old days, like when I used to do it, what you would do is you would synthesize, you would do your functional simulation or your architectural simulation. You generate a whole bunch of test vectors. You would generate that. You would test it. Then you'd make sure that it was functionally correct. You would synthesize your circuit. You would run the test vectors through it, and you would show that they were equivalent. Right. So now you've got the circuit. Now, in that process, I've made an assumption. Right. I've said in the FPGA, when it's doing the synthesis, all of a sudden it's grabbing, as you've just pointed out to me, the components. Right. It's instantiated a multiplexer. It's instantiated an AND, a NOR, and a flip-flop, and et cetera, right? That's because that's essentially equivalent to what happens in a standard cell phone, right? Where you've got a library, and what is happening is the compiler is actually grabbing blocks and instantiating them from that library, right? And essentially it says it grabs I need an AND gate, I'm grabbing an AND gate, I'm going to put it there. You know, I need an OR gate, I've got an OR gate, and I've got it in a standard cell process. And essentially what that has is that somebody's laid out that AND or NOR gate for you, right? And they've done it in such a way that they've minimized all the parasitics, they've minimized whatever in order for it to be, for the most part, as fast as possible for that particular process. But there might be situations where you want to make it run faster, right? So therefore you want to handcraft it. So therefore you might want to be able to design your AND gate a little bit differently, and we'll talk about why you might want to do that. Or you might want to design some of your other parts of your circuit differently because you want it to be, maybe not to run faster, but maybe you want it to be more power efficient. Okay? Now, just out of curiosity, I mean, this isn't part of on the lecture notes, we'll talk about it probably in the next couple of lectures. If you had a gate and was switching, or a transistor that was switching, what's the power that you consume? Does anyone remember? If you were charging and discharging a capacitor, how much energy does it take to charge a capacitor? It's what voltage, V. Does anyone remember a half CV squared? All right, so, and if you're doing this n times a second times frequency, usually it's a half CF V squared, right? So if you want to reduce the power, what's the most efficient way of doing that? Okay, I can make my transistors smaller, right? And if I make my transistors smaller, what happens to the C? It's proportional to area, right? So therefore, I get a linear gain with area, right? Frequency, I always want to run it as fast as possible. I can make it run a little bit slower, but I still get a linear improvement in power efficiency. I make it run, you know, lower in frequency. But where can I get my biggest gain? Voltage. Okay. Why? Sorry? All right. So if I go from if you go from, for example, if you went from 1.3 volts to 1 volt supply, you get a 69% improvement in power efficiency, right? So what that means is for certain parts of the circuit that you want it to be super highly energy efficient, you might have to design your own circuits and your own gates in order to be able to run them at 1 volts if it was a 1.3 volt process. Or if you're on a 1 volt process, make it run at 0.7 as an example. All right. So, and then, now I've forgotten why we've started this whole process. I was getting all excited, and now I've forgotten. So essentially what I was talking about was standard cells is, you know, it's essentially a library where you're doing the instantiation, like you do on an FPGA. Now, but on an ASIC, unlike an FPGA, you do have that extra choice of being able to choose how you implement that particular circuit, that particular logic gate, right? And that can give you some very significant advantages in terms of speed and also power consumption, which you don't have available to you on an FPGA. An FPGA, it's flexible, but I can almost guarantee you it's very, very power inefficient. But it costs you $1,000 to buy one. To make one chip, it might cost you 25 million, right? But you make many, many of them. Okay. So what we're going to do now is talk about how do we do this. Jeez. Work at this linear delay for these much more complex circuits. So what we've shown so far is the RC delay is shown to be a linear function of the fan out. So what we showed was, if you remember the NAND gate we had connected, or the inverter, and we connected in inverters. Essentially, what we said is that RC delay depends on how many of these other gates we're actually trying to drive, right? And there's a model that people have come up with called the linear delay model, and it of course has limitations, and I'll bring all this up, I'll put them up, I haven't put them up yet, I will definitely put them up, right? So don't stress, I'll definitely put them up. So what we've got is the delay is equal to the parasitic delay plus the effort delay, right? Now these are all definitions so far. So the parasitic delay is essentially the amount of parasitic capacitance and the delay that you get through that particular gate without anything being connected to it, right? And then the effort delay is actually the amount of effort or the delay caused by the gate complexity, which is actually the logical effort, and we'll talk about that in the next little while, times the fan out, right? And then the fan out, sometimes people refer to this fan out as electrical effort, right? And the electrical effort is again defined as the load impedance, the load capacitance the ratio of the load capacitance to the load, to the input capacitance. Right? So that's the definition of the electrical effort. Now, what we'll do now is let's start looking at the logical effort of some of these more common gates. Now, at the moment, all I'm doing, so just so that it doesn't confuse anyone, is we're making some definitions, and we're going through a process where we're trying to develop some machinery in order to allow us to analyse more complex circuits, right? So the Elmore delay that we were talking about previously allowed us to work out semi-complex circuits, but if you start getting more and more and more complex circuits, and it becomes more and more difficult in order to even apply the Elmore delay. So what we're doing is we're defining some new machinery which allows us to, get a sort of an approximation. It gives us some intuition into a particular circuit that we're looking into. So we've defined the delay to be the sum of the parasitic delay plus the effort delay, and we've also defined the effort delay to be equal to the gate complexity times the fan outs. And what we've said is gate complexity, what we're going to do is we're going to redefine it, or we can also call it logical effort. In some books it's called logical effort. And then we've got fan out, but sometimes we might not have the same number of copies of the same gate connected to the output. So what we're going to do is we're going to redefine, instead of using fan out, what we're going to do is redefine a new concept called electrical effort. And electrical effort is just, as I've just recently defined, is the ratio of the load capacitance to the input capacitance. Now let's look and define logical effort, and let's spend the next couple of minutes talking about logical effort. Now, logical effort is defined as the ratio of the input capacitance of the gate to the input capacitance of an inverter that can deliver the same current. That's just a definition, right? So, but intuitively, what it's really saying is how it essentially indicates to us how much worse that particular gate that we've got, an AND or an OR, is at delivering current or producing output current relative to a standard inverter. Okay, that's what logical effort actually means, right? Or the intuition behind it. Now, what we're going to do next is, it's usually hard to actually determine logical effort, and usually what we're going to do is we're going to, people do simulations, and a lot of times what happens is in these standard cells in the manuals, what you've got is you've got a table or a list which indicates some of the logical effort of some common gates, right? And like for example, on an exam, I might give you this table, right, as an example, right? And what I'm saying here is that there's a couple of things that I wanted you to note. Here I've got the gate type, right? So like for an example, an inverter, an AND or an OR, a tri-state or an XOR or an XNOR. Across here I've got the number of inputs, and here in each of these elements in the table, I'm working out the logical effort for each of these gates, right? Or not working out, I'm actually copying because somebody else has calculated these numbers for me, and I'm actually just putting them in the table for you, right? Now, what are some of the important things that you should note? Well, other than the number of inputs, and as you can generally see, as the number of inputs increases, the logical effort also increases. But the most important thing here is to realise is that XORs and XNORs are very expensive, delay expensive devices, right? So the point here being that even though, when you're doing, your Carnot maps, remember when you're trying to determine logic from a particular, truth table, like when you're doing your Carnot maps, the simplest circuit isn't necessarily the fastest circuit, right? And what I'm showing here is that, and we'll do some calculations and some examples in the next little while, is that in most cases, if you can, try to avoid using XORs or XNORs, because they're almost, 3 times as expensive as a NAND or something, right? So you can actually start building it with different combinations and get some performance advantages. Okay, so this is, again, a table of the logic effort. And what we'll do next is we'll talk about parasitic delay, because what we said was essentially the total delay is parasitic delay plus effort delay. And what we did here was actually go through and work out, in the effort delay we said it was logical effort times electrical effort. We talked about logical effort, and now what we're going to go through is go through and discuss a little bit about parasitic delay. Now, I mentioned it very, very briefly, that parasitic delay of the gate is the delay of the gate when it drives zero load. Right? And essentially all I'm saying is you've got a gate and you switch it on, you go from one state to the next, nothing connected to it. What do you expect this delay to be? Now, the other thing that's important to mention here is that all of these numbers, including the ones when I'm going to talk about on parasitic delay, I'm making them all relative to a simple inverter. Right? I'm making 1 unit is an inverter. Right? So therefore, what I'm saying here is that a NAND gate is 4/3 worse at producing current than an inverter, or an XOR is 4 times as worse as producing current as an inverter. So everything is relative to an inverter, right, on that particular process. Okay. So what we've got is the parasitic delay, and what we've said is, when we were calculating the Elmore delay, what we did is we worked out, what the delay was going to be, and we said, well, it was related to the diffusion capacitance. Now that's a very, very crude model, but that can give us some insight into the the overall diffusion capacitance of the output node, and also the resistance. Now, what I'm going to do here is essentially go through the process, or give you another table where we're actually calculating the parasitic delay of some common gates, right? So therefore I've got an inverter, which I've got 1. A NAND gate has got twice the parasitic delay, NOR, and as we increase the number of elements, we can actually see that we get an increase in the parasitic delay, as you would expect, because as you increase the number of inputs, you also expect to have twice as many transistors, so therefore that gives you an increase in the overall parasitic delay that you would expect through that circuit. But some things that you've got to be a little bit careful of, just to have in the back of your mind, maybe good in practice, but not necessarily important for this particular component of the course, but again, important to have in the back of your mind, is that in theory, increasing the size decreases resistance but increases capacitance, so the product's usually constant as RC. But the truth is, larger transistors can be folded, so therefore there's less than a linear increase in parasitics, right? So it's not necessarily true that a larger capacitor will give you, a larger transistor will give you the same parasitic delay if it's larger, right? Because you can actually fold it, and therefore you get a less of an increase. That's just a little background knowledge to have in the back of your mind when you're doing it in practice, right? Maybe not important for this particular course, but good for when you're practicing as engineers. Okay, so now let's start putting this into practice. Okay, so what we've got is we want to look at a logic gate. So let's all of a sudden, not all of a sudden, let's, for the heck of it, look at a ring oscillator. Now, who can remember what a ring oscillator looks like? Let me do that. If I asked you to build a ring oscillator, has anyone built a ring oscillator? No? Okay. Has anyone seen if you put two or at least, three of these inverters in series and you connect the input to output, what do you imagine will happen? If it's called an oscillator, what do you expect is going to happen? It's going to oscillate, right? Okay, so usually on a lot of processes, if you want a cheap and nasty way of being able to build an oscillator, you would build a ring oscillator. Can anyone imagine the challenges or some of the problems, other than the delay that we're going to talk about here and how to calculate it, some of the challenge? Why wouldn't you try to build a good oscillator, or why wouldn't you build a ring oscillator like this in practice on your chip if you wanted it to operate at a particular frequency? Yes?
There's just like a maximum frequency at which it can invert depending on the delay included by each gate. So
yes, it depends on mobility, it depends on a whole bunch of things, right? So therefore it changes, it depends on your doping in your of your wafer. And usually what you do is, if you want to work out on your particular process, right? Because you probably, I don't imagine you've probably seen this before, but when you're producing chips on a wafer, some areas get more doping than others, right? So therefore the center, you're doing implantation, it's more phosphorus, more boron, so therefore the transistors are going to operate faster towards the edges and they're going to operate a little bit slower. So one of the problems is you don't really know, if you're producing a chip, how much of the good stuff, let's say, it's actually gotten, right? So one of the tricks that you can actually do is you can actually put, build a couple of oscillators, ring oscillators on there, right? Either and by looking at the speed of this oscillator, you can actually work out on which corner you're at, right? So therefore, if you're on fast, right, you would expect the oscillator to operate at a faster speed, right? I guess you guys don't know about corner skews and things like that, and no? All right, let me forget about that. Let's talk about, hey, we're going to build ring oscillators. If you put a whole bunch of inverters together and you connect the input to the output, they oscillate, right? And depending on certain characteristics of this of the process, you can actually work out how fast that particular that particular structure is going to oscillate. So let's go through the process of using the machinery that we've just learnt in order to calculate what what is the speed at which this thing is going to operate at. If we had, for example, 3 or 4 or 5 or 6 inverters, how fast is it going to operate? Okay, so here we know for any particular process that the parasitic delay of an inverter is defined to be equal to 1, and we also know that the gate complexity is equal to 1, and we know in this particular case that any one inverter is connecting to one other inverter, right? So we had our formula for delay, if you remember, and it was was parasitic delay plus effort delay, and we said that effort delay was gate complexity times fan out. So in this particular case, what we've got is the delay is equal to 1 times 1, which is 2 units of delay, right? So what you can then do is you can actually say, well, if I'm going to be going from, here, in order for it to go for 180 degrees phase shift, so for example, I'm going from a positive to a negative and a negative to a positive to actually get one period, I need 2 times the total delay, right? And if I've got n stages, the total delay is n d times 2, right? And we know that the delay in this particular case is 2. So what we can actually do now is work out that if we were building an oscillator, a ring oscillator, using this process, what it would do is it would oscillate at a frequency on 1/4 for n. Right? So what have I done? So all I've done is I've connected these inverters and I've said I've got n, right? Because I might not want a particular frequency. I'm just doing it in general, so I can say if I wanted any frequency, I can add more and more inverters. What would be its period if I had n of them, right? So essentially what I'm saying is I've got a delay, the total delay from 0 to 1 transition is d units, whatever d is here. But I'm also going to go from 0 to 1, 1 to 0 in order to get 180, to get one full period of 360 degrees, I should say. So therefore I've got 2d delay, I've got n stages, right? So therefore my total delay is 4n. So therefore the period is 1 on 4n, right? Where n is, you've also got to have the delay through one inverter. Yes?
Why is it 4n and not 2n?
Oh, okay. Okay, so remember the delay is 2 units, right? And then what I'm saying is I'm going to go from a 0 to 1 transition and a 1 to 0 transition. So that adds another 2, right? So therefore it's 1 on 4n, right? And then what I've got to do is times the delay through, how do you call it, through an inverter, right? And usually people give you this number, right? So therefore, if you can estimate it, I think in a 65 nanometer process, if my memory serves me correctly, that's probably in the order of, in the order of about 50, 60 gigahertz, right? So if you had n, you can get, so divided by 10, you get 6 gigahertz. Divided by 20, you get 3 gigahertz. So you can actually start, building some very interesting ring oscillators very quickly, and you can actually approximate very, very quickly what you would expect the frequency of oscillation to be. Right? And then also, as I said, you can also use this in order to work out, your doping profiles and which corner you are on a particular chip. And what I would suggest that you do is go home and look at skews, or process skews. Yes?
Is that T or F? Because that would mean that the bigger the number of oscillators, then the smaller the F.
Okay, yep. All right, okay. Yes. All right. So we're going to look at process skew. You're going to do it, go home and look at process skew so that you can actually work out what that all means. All right. Now, okay, so this has now given us a little bit of equipment in order to be able to work out what the propagation delay is going to be through any kind of circuit. And also what we've done is we've used it now as an example to work out if we had a ring oscillator on a particular process and we had n of these inverters in order to produce the ring oscillator, we know how fast it's going to be, or how fast it's going to oscillate. But now, what are the issues? I mean, can we continue to use this, blindly? And what are the limitations of this linear delay model that we're using? Well, there are some limitations, and what we'll do is we'll talk briefly about these limitations. Now, one of the first limitations is that we're assuming in this particular model that the input has a very sharp transition. So when it goes from 0 to 1, the slope of that 0 to 1 happens very, very quickly. Why is that an issue? Can anyone, by looking at this graph, tell me what they would expect would happen as the slope changes? For example, if this had a large capacitance and this didn't have sufficient drive in order to be able to get it to move quickly, what would we expect to happen? We would expect the transition from a 0 to 1 to occur much, much more slowly, right? And here what I'm showing is as the input changes, or in this particular case, the output here, the input also takes longer and longer, right? That is not captured in this linear delay model, right? So I guess what's important here is if you're using this linear delay model, there's the implicit assumption that you're making that all of your circuits have got sufficient drive in order to be able to produce very sharp edges, right? If you start getting into the situation where you've got some kind of slewing, probably is the best way of describing it, the model's not valid. Okay? Okay. Now, the other thing that the model assumes is that all the inputs arrive at roughly the same time. Right? So therefore, that's not necessarily a good approximation, but it's something that you just need to keep in the back of your mind. That it's a very interesting model. The linear delay model is a very interesting model, but it has some limitations. And one of the important limitations, other than assuming that there's fast edges on the inputs and there's sufficient, all the transistors, all the gates have sufficient drive in order to be able to drive the gates that are following, is that roughly all the inputs arrive at roughly the same time at the gate input, at any one gate input. And then also the other assumption is, or the other way that the other way that rewriting that assumption is to say that you're only assuming that one input is changing at a time, right? So you can either have all of them are occurring at exactly the same time, or only one is changing at any one time. Right? So if you rewrite it in that particular way or express it in that particular way, what you realise is it's a quite significant limitation, because as your circuits get much more complex, that hardly ever happens, right? And then what we talk about, what I'll talk about, some of the other limitations are of course related to, let me also say that when sometimes, it's not always that all the inputs changing simultaneously is a bad thing. When they're in series and you've got stacked transistors, that increases the delay. Of course, when they're in parallel, it decreases the delay, right? So anyway, that's just something else that you should keep in the back of your minds. Now, the other limitation is it doesn't take into account velocity saturation, and then also it doesn't necessarily take into account voltage dependence, right? And there, what I'm saying specifically is, as we started off this lecture, I started to talk about, hey, how about we wanted to improve the performance of the power performance of the power consumption of a particular circuit? One of the things that we could do is scale the voltage down, right? But what we're showing here is that if you scale the voltage down, you get a nonlinear relationship between the voltage scaling and the propagation delay. So that linear propagation model doesn't necessarily hold. So what you would need to do is you would need to calculate those propagation delays for a particular voltage, rather than saying, oh, if my voltage was this, I would get this performance or this propagation delay if I scaled the voltage by, 25% or, 30% down. All right? That's it. So let me stop there, because what I'll do is I wanted to talk about logic effort in paths and things like that. And we'll do that tomorrow in branching, so we can work out how to calculate that, and then also how to optimally size logic gates and transistors in order to get the best performance. And we'll talk a little bit about, the optimal sizing of gates tomorrow. And what I'll do is also put these lecture notes up so you can actually, how do you call it, see them while I'm actually lecturing. All right, cool. So, Will, have you seen you've seen all this, right? So you've seen all this before, right? No, this, all the...
Well, I think so, but it's sort of...
A bit different.
No, what I found is there's an element of I don't know what I don't know, and I figured I'd just come along,
Okay.
and if I've seen it before, I've seen it before, and if I haven't, and I don't think I've seen it like this.
Okay.
So this is more sort of Shane's work.
Yes.
It's out of my domain, and I might even learn something from it.
Okay, good. All right, excellent.
Yeah, it's down.
Yes.
I'm very confused about why this is missing.
Okay, that's what I was saying here. Let me show you. Okay. When I said what you would do if you were designing this, you would share the diffusion wells.
Yeah.
You wouldn't actually you wouldn't do it this way, right? So if you did it that way, what it's showing is I need to have another 3C there, right? I need to have 2. Okay, but that's a bad layout, right? If you were designing it using not real transistors that you were buying off the shelf, you're right. You would need to put another 3C there.
Yeah.
Right, so you need to put 3C. But if you're doing it a layout on a chip, you can actually share the diffusion wells. Does that make sense? Let me draw on the board for a sec. Yes, I think you can actually see what I'm saying. Give me a couple of okay. So when you've got a chip, right, you've got a P substrate. Lately, okay, you're trying to build an NMOS transistor, right? So what you do is you implant okay, let's see if that one works. Alright. Yay! Alright. So you implant in here. And then of course you put in plus here, right? So you can get an ohmic contact. Let's see if that works, right? Alright. Okay, and what you do is alright, so this is how you would build a little transistor on a chip. Okay, and then what you do is you put some oxide here, and then you put your, and then you put your gate. Right. So this is your transistor, right? You've got a contact and a contact. Okay. Now, you can do 2 things, right? You can do the wrong thing, and let me show you the wrong thing, okay? Which gives you twice the capacitance. Which will give you the, no, not this one. The one that will give you 3C and 3C. One of the things that you can do is someone's not okay. This one's broken. I'm on video now, so. Alright. Okay. So you can do this, right? And then what you do is you would connect this together, right? And you connect them. But you see now you've got capacitance 1, capacitance 2. if you're laying out the chip yourself, right, what you can do, because it's the same thing, just make it the same well. Right? I mean, I haven't drawn it properly, right? So therefore, what you've got is C1, 2, C2, right? So therefore, it's just you want to see, right? So you've saved yourself the capacitance. So therefore, by doing this trick, you've now got your circuit runs much faster, right? And it's a layout trick, right? And that's why I was trying to emphasise it's a layout trick, and that's why I've got half the capacitance. Now, but if you were, for example, buying transistors, right, instead of building a chip, what you have no choice, right? You would buy the transistor, and then you would buy another transistor. You got no choice. Then when you connect them up, it's like connecting the previous one. You have C, you have 3C and 3C. You know what I mean? So all I'm trying to do is give you a little bit of insight into, hey, if I'm really building this, and really when you go high speed electronics, you would never do this. You would only do this if you're building something slow, maybe high voltage. Right? But if you're doing this, you would always build it on a chip. And what you would do is, if you're building it on a chip, what I'm saying is make sure you don't do something silly by adding 2 diffusion wells when you don't need to. That's what it is. Okay?
And here, right, 9C and in the top group it should be 7C here.
I might have made a mistake then. Okay, so have a look.
But I think 9C is right because
They've made mistakes in the textbook. I actually do the maths when I do it. Now the problem is I can also make a mistake. But yeah, I think it should be 9C. But it's a really nice book. What I suggest is after the course, maybe go to the beach, have a coffee, and just read it. I mean, it's a really good book, and you learn. It's got a lot of very interesting stuff in there. And nobody, if you're doing all the high-speed digital, this is all the stuff that you're doing. It's all VLSI, and this is what you would do, and you need to work out the propagation delays and all that kind of stuff. And this will give you the foundation to understand your design. The other thing I would suggest, if you can, look, I know you guys get home, just grab DC compiler from Synopsys. DC compiler. So what it does is it converts Verilog into a net list. Right. What I would do is there's maybe some standard cells for a particular process. We'll look at maybe, I think SMIC, which is a Chinese semiconductor company, has got a process and some standard cells on their website. Download it, put it through, do a couple of simple circuits, and synthesize it. Actually get some experience doing it, right? You know what I mean? This is a Synopsys tool. So Synopsys, you can also, I forget what the cadence one's called, but these are digital synthesis tools. This is digital. It converts Verilog to a net list, and then it gives you timing, and it tells you all the path delays and which one's the slowest nets and all that kind of stuff. So it actually puts into practice all the stuff that we're talking about. All right. Don't ask difficult questions.
No, very simple for you. So when we draw the equivalent RC module like this, why we don't count the capacitance at the base?
Capacitance at the base.
I mean, it should be a capacitance parallel here, right?
So, we don't compare it at the base because it doesn't change. The voltage doesn't change.
Why?
Because it's always, that one's tied to ground.
But this one, like Yeah, I know what you mean, like this one, right?
No, that one, yeah, that one, yeah.
That one doesn't change
Yeah.
because both sides is connected to
Yeah, yeah.
VDD.
Yeah.
But that one is connected to here. I mean, the base